Okay, thank you. Is the lapel mic on?
Yep.
Yes.
Thank you very much for this honor. I should thank the Academy. I guess that's a different award. But I'm incredibly thankful and gracious and really humbled by this award. I'm humbled by this award in part because of the great people that have preceded me. Those shown in red are people that I've known from Maurice Wilkes to my graduate student office mate, Susan Eggers. And it's quite an honor and humbling to have your name associated with the likes of these people. I didn't really know Eckert-Mauchly. The closest I got was standing in front of their machine, the ENIAC, a few years ago with my PhD student, then professor at UPenn, Milo. Now this award is really not about my work though. This work is about our work. I have 160 co-authors that contribute to this work. None of it is really mine. I'll come back to this word cloud later. But it's a work of many, many people. It's also a work on sort of many topics. And so with all these topics, I can't, appropriately go into the many topics. And so what I want to do instead is talk about and give some useful advice about how I think are good ways to conduct research. And I'll use some examples from the past, but try this to be a lesson going forward. So among the most important methods in computer architecture is simulation. Tycho and De Niro were some programs that came out of my PhD with David Patterson and Alan Smith. De Niro was a uniprocessor cache simulator used at dozens of universities. My later students will be amused to know that I couldn't find a graduate student to write it, so I actually had to write it myself. After we became professors, though, Jim Laris, David Witt, and I, with student Steve Reinhardt, were really interested in getting shared memory multiprocessors to be simulated at a nice high speed. And we developed something called the Wisconsin Wind Tunnel, which simulated a shared memory computer on a non-shared memory CM5. And this was a really cool device, but it had a couple of limits. One limit, it was hard to give this simulator to other people because most people didn't have the CM5. The other thing is that the CM5 never got faster, and Moore's law was operating very quickly, and so the simulator quickly became obsolete, and so we decided we had to go software only. The other thing that happened was that we got a lot of feedback from industry, and I'm very fond of getting feedback from industry in industrial affiliates meetings and other things, that commercial workloads were important, and it was also very important to run the operating system, not user-only simulations. And so we developed something called GEMS, with the lead student being Milo Martin and Dan Soren. But we were kind of creatively lazy people, right? So modeling performance at various degrees of fidelity is relatively easy. But getting the function right to actually boot an operating system and run I/O drivers is difficult. And so for that, we leveraged Symix out of Virgitech. And that worked as a good symbiosis. But once again, that had a limit because not everybody wanted to license Symix. So the next step was to work with the M5 people, who Steve Reinhardt and Nate Binkert weren't afraid to get the function right, and symbiotically combine to the Gem5 simulator, which now has spread to many places, and it has reached the exalted point where it's cited a lot. It's even cited when people are explaining why they're not using it. So you might think that the most important method in computer architecture is simulation, and the slide seems to confirm that. But it's actually much more complicated than that. Simulation is a really excellent technique for testing and refining hypotheses. But this is actually the last step of the scientific method. It's the step in the scientific method most visible in papers. So if you're new to the field, you think this is it. And I want to talk about some of the earlier steps because I think they're critically important. So Francis Bacon in the 1600s did a good job of articulating the modern scientific method. This is a picture of his book. There's a modern technology of the time, a galleon sailing through the Pillars of Hercules at the Straits of Gibraltar. But this really was that profound. It helped create the modern world. And as I said, the last step of this is testing and refining hypotheses. Before that, you have to have an insight and you have to have a first hypothesis. Where does that come from? And before that, you need to pick a problem. Where does that come from? We're going to talk about that. And finally, I know it drives students crazy when they want to talk about in their paper all the meandering turns they took to find something, and the professor says, no, you've got to write the straightest path to explain it. But these steps and these iterations are a necessary part of research. Before I leave the scientific method, I highly recommend this book, this paper, Strong Inference in Science, from 1964. Still a timeless classic. Okay, so what I'm going to do in most of this talk is I'm going to talk about insight and first hypotheses using 4 examples of our work from 4 different decades. And we'll talk a little bit about picking a problem and giving thanks. Echoing a lot of what other people said. All right, so in the 1980s, there's a picture of me. It's amazing. 4 decades, no difference. We were fascinated with caches and virtual memory, right? These are things that we engineers create where the system is better than the technology levels it's being created about. And there was at the time, and there still is, a data deluge. And so how does one make sense of this? And could we do better to make sense of this? Was this a good problem? Well, it turned out it was a good problem. I can't say we picked it for a good reason. Sometimes it's serendipity. But really wanted to get some more insight. Richard Hamming says the purpose of computing is insight, not numbers. And as Sandia was saying, we developed the 3C cache misses. This is with David Patterson and Alan Smith, my PhD advisors. Conflict misses when you don't have enough associativity. Capacity misses when you don't have enough size. And compulsory misses because you haven't seen it before. I should note this graph from my thesis goes up to a whopping 8 kilobyte cache size. Now when you do work and people read your work and it might give them insight, you often don't ever know that you propagated some insight because sometimes even the people who have the insight following on you don't even know. But in this particular case, Norm Jopi a year later explicitly credited us in his thoughts on victim caches and stream buffers. And then later on, the idea got put into an undergraduate textbook. Now, it's super convenient, and I recommend this, is to have a PhD advisor who co-authors the undergraduate textbook. One of my proudest moments as a professor and a father was when my son snapped this picture taking a computer organization class at Cornell. And Hakeem Witherspoon had put up the 3 C's, I guess you can't see it very well, on the projector, and it was now sufficiently well known that no name had to be given with it. So, very satisfying. So all that came out of trying to get some insight, trying to use a taxonomy, trying to make sense. Even though 3 C's is too simple, and in fact in many ways it's wrong, it's still helpful. Second example I want to give about methods and with an example from research comes a decade later in the 1990s. So David Wood and Jim Laris and I were sure, I guess this was before David Wood actually, this was work with Srita Adbe, sorry. We were sure that shared memory processors were here. Well, it turns out we were wrong by about a decade. But one of the great things about doing research is that you have to predict trends, but you don't have to necessarily predict timing. Right? If you're doing a product, you have to predict timing. And one of the things we noticed was there was all this activity with coherence. And when you're done with coherence, it made the caches invisible. Well, what were you left with? Well, there were some ideas out there. On one hand, Lamport had defined this beautiful theoretical model of sequential consistency, which said that things behaved like that simple switch over there, which was great, except almost no machines actually did that. what actual machines did were much more complicated. They had write buffers, out-of-order execution, and what we now call atomic stores. Very complicated. So you had the simple but irrelevant, and you had the complex reality. So what to do? Well, Albert Einstein says everything should be made as simple as possible, but not simpler. Okay, and so we decided to start thinking about this. And one of the origins of this was a talk by Bart Miller or his student Rob Netzer on software data race detection. And after hearing this, it seemed like it smelled like there was some connection between data races and relaxed models. So the lesson there is for insights, go to talks in related areas. Like Kevin talked about that too. And so Sarita and I eventually, after much hard thinking, it became simpler, developed sequential consistency for data race-free programs, which, as you remember, presents the simple model of sequential consistency for a subset of programs that don't have data races, but yet still lets the hardware do all that crazy stuff. And this showed up in a paper in 1990, amazingly in the same session that release consistency was in, so that was quite a session. And Sarita took this idea further, working with others, and moved it to the high-level languages of Java and C++. And then more recently, there's been some controversy going back and forth on whether you can use this idea or you have to go to something more complicated to understand GPU coherence. A lot of good work, a lot of influence, all coming from sort of a simple insight that there seems to be a relationship between data races and relaxed models. The third example I want to give, going forward another decade, is we once again believed that shared memory multiprocessors were here. And it turns out we were right, but not really, we didn't really know the right reason. The reason was that the Dennard scaling ended, so they finally happened. What we also thought was that it was very important to ease the problem of multi-threaded programming. That if you had to program with locks, the locks don't really compose and you risk deadlock. And we thought, actually it turns out incorrectly, that almost everybody needed to program these machines. As we know now, many people can benefit from these machines, even like in the cloud, even though few are programming, but we thought it was very important that many program, and some do have to program. And we love this nascent idea of transactional memory, where the programmer said, make this atomic, and the TM system said, yes, ma'am. And there were some early systems, such as Hurley and Moss, and TCC, which had plenty of flaws to inspire us, and UTM, Christy is also here. These are really good early systems that were provoking things in very different ways. And what we really wanted to do was to make sure that things like the write buffer size and the cache associativity was hidden from whether transactions would commit, that they affected performance but not correctness. And we wanted to do more modest changes than some of the early proposals. And I know modest can sometimes be considered incremental, but incremental can also facilitate adoption. So how do you possibly do this? Well, we went to another technique that we have found very effective over the years, and I highly recommend, is do a taxonomy. We saw a taxonomy in Jim Smith's talk the other day. And so in this case, this was a taxonomy of transactional memory systems, which had two dimensions, conflict detection and version management. In conflict detection, you had to look at concurrent transactions doing reads and writes and see either eagerly write when they did a read or write if there was a conflict, or lazily wait till the end of the transaction and detect. And orthogonal to this was the version management, where all transactional systems have to keep the new value if the transaction commits, and the old value in case the transaction aborts. And the lazy system doesn't put the new value in place until you're sure you're going to commit. The eager system said, hey, I think we're going to commit, let me squirrel away the old value on the side. And so this taxonomy let us explore where database management systems often were and develop the LogTM system with David Wood and Kevin Moore and Mike Swift and others. I know some of you might be saying, like, what the hell is TCC getting this award and Mark talking about LogTM? This stuff really isn't that successful yet. Well, first of all, it's more successful than you might think. There are TM systems adopted by IBM and Intel and recently ARM. And also, I take sort of the long view of research. And as an example, let's look at Cindy. Cindy had a 3 or 4 decade gestation period as niche successes before the much more broader success with SimT. And so a similar thing could be happening here. More generally, I highly recommend taxonomies for provoking your thinking. Let me mention what I consider the mother of all scientific taxonomies, Mendeleev's periodic table of the elements, which allowed chemists to focus on things that were missing and actually discover new elements. So taxonomies. Okay, forward another decade. This is the 2010s, and systems on a chip, or SoCs, have sort of really grown up. They have CPUs, big and little, they got GPUs, they got many accelerators, interconnects, coherence, virtual memory, virtualization, plenty of stuff for architects to love. So I went on a sabbatical to Google's Mobile Silicon Group, and Albert Mexner, a student of Dan Soren, was my manager, such as I can be managed, and said, you should make SoC design more scientific. And my reaction was, gasp. Right? That's a real easy task for a few people to do in a few months. And so we started to think about it. This was with Vijay Janapan Reddy. And like, how do we make some progress? Well, we got to simplify. We got to get a toehold on this problem. Okay? But we also, have been teaching out of Hennessy and Patterson for years and years, and we know part of really understanding what the hardware is to understand what the software is doing. And so let's look at the software. And this is a figure from one of Vijay's papers that preceded me of recording 4K video on an SoC. Now the details don't completely matter. The squares represent various accelerators, and what you see is for recording 4K video, many accelerators are used, and some accelerators are used more than once. What's not apparent from this figure is they're used concurrently. There's a lot of pipelining of the data, and it's all choreographed by the CPUs, not shown. The other thing that I found really interesting about this is that there's a lot of data, and the data passing between these various accelerators went off chip into DRAM and back for a half a dozen round trips. And so it wasn't exactly clear, are you going to be compute bound here, or are you going to be bandwidth bound? And what we came out of this was that there's a lot of accelerator level parallelism, but we got to get a handle on this bandwidth. And this is a recurring theme, right? It's not just compute, it's also storage and bandwidth. So to get a handle on this, we also tried to go simple and try to do a model. This is not simulation again, with something called the Gables model. Now, Gables is a roof with many roof lines, and that's because this builds on a roof line. So a roof line is a picture like this, which looks like a roof line that has a trade-off between whether you're bandwidth bound or whether you're compute bound. And originally it was proposed for one roof line for an entire multi-core chip. And we found that it could be applied to the CPUs shown in green here, and then you could do a whole bunch of other roof lines for the various other accelerators. And you could characterize the SoC with not just two parameters, but more, some bandwidth, some accelerations, and then the software side, had a fraction of work assigned to each accelerator, sort of a generalization of Amdahl's law. And there's a really cool parameter from roofline called operational intensity, which tells you whether or not you're in the bandwidth side or the compute side. And I was struck how many times the engineers were not exactly sure the order of magnitude of their operational intensity. So is this a good model? Well, first of all, it's wrong. All models are wrong, some are useful, and whether it's actually useful, time will have to tell because it's only a year old. But I do think it gives you a way and a toehold to think about things. And more generally, even if you don't care about SoCs, Vijay and I believe that accelerator level parallelism is going to spread much more widely. Because there are many places where you need performance, such as you're doing machine learning, and you got to do it at the same power without a lot of technology scaling. And using many accelerators in parallel, I would argue, is one of the few techniques out there. And we can put this in context of a long time period. Here's a graph showing time from 1940 to the present. And early in our toolbox was bit level parallelism, instruction level parallelism. And then around 2004, shown in red here, Dennard scaling really interfered with exploiting more instruction level parallelism. And this finally allowed thread level parallelism to really take off, going from black, representing the niche markets, to green, representing ubiquitous use. 10 years behind it, we had a similar effect with SIMD data level parallelism in GP, GPU, SIMT. And we are predicting that 10 years beyond that, accelerator level parallelism is going to go from the niche market of SOCs to be more commonly used. All right, well, by the way, and that sounds great, but we know how to do a model of accelerator parallelism. We don't really know how to do the systems that well yet, and I charge you to work on that. Okay, so that's the longer part of the talk about first insights and first hypotheses. Working backwards, before you start asking for an insight or a first hypothesis, you have to pick a problem. Okay, and this is one of the things that's really hidden in the paper. It's kind of assumed that there's a problem. Where did this person come up with the problem in the first place? Okay, in my opinion, the best way to pick problems is to pick problems that if you can solve it, people will care. A counterexample of this is to play Jeopardy. Jeopardy is an American game show where the answer is on the board and you guess the question. And you might say, well, no one would ever do that, but you actually see that sometimes. People have this cool mechanism and they are looking for a problem that it can solve. I say start with the problem. Now, this criterion here, if you can do it, people will care, is not sufficient, because showing that P is not equal to NP qualifies for this bullet, but most of us in this room are not qualified to answer this. So the second criterion is you have to be able to do it, or at least do some of it. Okay, and so the happy space is a problem that people will care about, and something where you have reason to believe that you can make progress because of the skill sets that you have or others that you're working with. Okay, so this is not completely operational. How do you then look for problems? Well, I think a great place to look for problems is to look for changes. Right? Look where there's like a new technology, non-volatile memory. Look where there's new computer use, these SOCs doing augmented reality. Look where other subfields have done something totally different. You know, program synthesis and SAT solvers have made tremendous progress. Because if you look for changes, you don't have to be smarter and more creative than 3 decades of people before you. You can be working in a green field. So let me give you an example of this, which just sort of bowled me over when I was a grad student. And it wasn't done by me, it was something that I observed. So Patterson, Gibson, and Katz developed RAID, or redundant array of inexpensive disks, which I think most of you are familiar with. Okay? So a cool idea is you got these erasure codes, they're done on the blocks, you rotate the blocks so the parity disk doesn't get overwhelmed, and you say, man, that is creative. That's really creative. Well, in my opinion, by the way, that is not the most creative part of the work. The most creative part of the work was recognizing the problem, okay? And let me run you through that, because I watched it happen. So, in the couple decades preceding this work, the most cost-effective place to store a large amount of data was on a really large mainframe disks. And these disk packs were like the size of washing machines, okay? Personal computer came out, and after some number of years of floppy disks or worse, they started to get little hard drives. And what happened was a flip, where the cheapest place to store a bit were on the personal computer disks. And so a question you could ask then, and they did ask, is could we use a whole bunch of these PC disks to store the large data? Well, the answer was no. Because the personal disk individually was not reliable enough, because the market was not an enterprise market. And secondly, once you put a whole bunch of them in parallel, they really failed way too fast. So we could do that if we figured out a way to make them more reliable. Hence, you invent the erasure codes, right? This was like, once you got to that point, the erasure codes and the RAID work, it was practically a jigsaw puzzle to be solved. So in my opinion, the creativity, the biggest creativity, was recognizing the problem. And so I encourage you to spend a lot of time thinking about picking the right problem to solve, because that's where you can really have leverage on your impact. I also am a big fan of simplicity. Norm Jopi was complaining about people using complex method. This is from a subpage on my website. It says, many academics strive for complex solutions. I'm proud of my simple ideas. This predates this award and this talk. And some of them are like applying Amdahl's law to multi-core chips, cost-effective computing with David Wood, and some of my thesis work on showing direct map caches can be better than set-associative caches. The tagline for that, by the way, when I was interviewing is big and dumb is better. And I had to convince my wife it wasn't talking about me. The other way to do really good work is to collaborate. Okay, so this is a word cloud showing the logarithm of the number of papers somebody wrote with me, and of course David Wood is the leader, a little bit north of a third of the papers. Notice also that there's a lot of collaboration with people who are in other areas. Jim Laris in sort of programming languages, and Mike Swift in operating systems. Collaborating with other people is just a really great way to have ideas. You of course collaborate with students, but collaborating with other colleagues, and don't worry about dividing the credit. If the credit is good enough, it really does multiply. The other thing that I have found very effective is keeping connections with industry. For a long time, Wisconsin's had an industrial affiliates program, and I've also found it effective to do sabbaticals in industry. Now, sabbaticals in industry are a very time-consuming thing, but they can be useful. I know some people say, don't do that. You can't take away industry solutions, you just get in a proprietary rat hole. It's correct, you can't take away the solutions, that's their intellectual property, but you can take away problems. Problems that are just emerging, problems that are being band-aided, problems that are not really the key problem on this product, but your intuition says they're going to get a lot worse. And so we've done this a couple times. There's a sabbatical at Sun Microsystems, working with Eric Hagerston, David Wood consulted on this, and we recognize that the academic literature, represented coherence protocols with like a 4-state finite state machine. That's not where the real problem was with coherence protocols. That's like the instruction set of coherence protocols. The real problem with coherence protocols was in the microarchitecture with all the transient states and messages. And this led to this primer on coherence and consistency, which has actually been downloaded 9,000 times, which tells me that bots love this subject. By the way, since I'm still in academic sales, Vijay Najaran and we are doing a second edition. We're adding GPU coherence and pointers to some of the great formal methods works that's happened since this book. Next industrial sabbatical was at AMD after they had bought ATI. Very interested in GPUs, GPU, general purpose GPU computing, coherence and consistency of GPUs, and also with cooperation with the CPUs. And then there's the Google sabbatical that I mentioned already. All right, so it's been a long process. I'm the first person in my family to get a bachelor's degree, so it's a credit to, I think, the environment in the United States that this is possible. Here's my 9th grade science fair project, which is a mechanical byte adder using address labels. So people probably wondered why all the zeros and ones were gone. And I've been privileged to be associated with some great institutions, Michigan undergrad, Berkeley grad student, and Wisconsin as a professor, and most of my funding come from the National Science Foundation. All right, but in a larger sense, it's a long tradition, and we don't stand here today without a lot of people behind us. And we were able to connect my academic genealogy way back, and my daughter Nicole, who's a graphic designer, did a nice poster, which you can go to that link and find. So a real genealogy has your parents and your grandparents. This one has your advisor and your advisor's advisors. Goes back to 990 AD in Constantinople. Okay. It includes two saints, which are not my advisors. Copernicus and Helmholtz, and then of course my very esteemed advisors, David Patterson and Alan Smith. And one of the greatest things about this poster is I can add another level to it and give it to each student when they graduate. And when they have a bad day with some paper rejections, where reviewer number 3 is hard on them,